1.7, inequalities. In this final installment of dealing with inequalities, we're going to deal with rational inequalities. So we've dealt with linear inequalities, which we just kind of solved as it was. We dealt with quadratic inequalities, which we just turned it into an equation, solved, and then created intervals. And now what we're going to do is we're going to deal with rational inequalities, so where you have that polynomial or another polynomial, or any sort of grouping like that. Now with rational inequalities, what we need to do is, as necessary, we need to get 0 onto one side, everything else onto the other side, and we want to get it so that we have just one rational function on the other side, meaning that we don't want something in the form x plus 2 over x minus 3 over 2x greater than 7, or even if we put it to 0. We don't want it like this. We want something in the form x minus 3 over 2x squared. That is not this, by the way, just to point that out. Okay? But we want it so that we have one rational expression on one side and a 0 on the other side. So that means finding common denominators and doing the work necessary to turn it into that. Now, once we have it in this state, then what we're going to do is we're going to find all the roots of, or solutions of, the numerator and the denominator. So we're going to find all of those, and just like we did with the quadratic inequalities, we're going to use those roots to create intervals. And we're going to try a value in each one of those intervals to see which of those intervals get included. Now, the difference with this, though, is that if it's a strict inequality, just like with quadratics, then we don't have to test the endpoints. If it's not a strict inequality, if it was greater than or equal to, then we have to test the endpoints of each of our intervals, except those endpoints that came from our denominator, because we can't allow those endpoints or those zeros to be the value, because it would give us a divide by 0 situation. So if we have a strict inequality, we have to take any endpoints that came from the numerator and test those to make sure they work. Now, in general, you just have a strict inequality, then none of those endpoints are going to be included. If you don't have a strict inequality, then generally, yes, the endpoints of the intervals that work, those endpoints will also be part of it and be included. But it's always good to check just to make sure. So let's do an example, because just like quadratic inequalities, this makes a heck of a lot more sense when you actually start doing it. And try an example. So we're going to start with one that's relatively straightforward. 6 over x minus 3 greater than or equal to 4. Now, as I said, we want to get 0 onto one side, and we want to get a rational expression on the other. So I'm going to subtract 4 from both sides. So we get 6 over x minus 3 minus 4 greater than or equal to 0. So that's good. We got 0 on one side. But now we need to turn this into one rational expression. So I've got x minus 3. This is over 1. Common denominator, x minus 3. 6 minus 4 times x minus 3 over x minus 3 greater than or equal to 0. If you're asking what I did there, well, just remember, to get this over x minus 3, I'm going to multiply the top and bottom by x minus 3, and then I've got a common denominator. So that's all I did. I kept the common denominator instead of taking that extra step and going 6 over x minus 3 minus 4 times x minus 3 over x minus 3, I just put it over there because that's where we're going to want to go eventually anyway. Now what I do need to do here is I need to multiply this out, so distribute that negative 4 through, so I can combine like terms and determine whether I have any other factoring to do, but at least I can get it to where I can get the 0. So 6 minus 4x plus 12 over x minus 3 greater than or equal to 0. Negative 4x plus 18 over x minus 3 greater than or equal to 0. Now we can look for the zeros of these, meaning that we'll set negative 4x plus 18 equal to 0 and x minus 3 equal to 0 and find out what those solutions are. So negative 4x plus 18 equal to 0, negative 4x equal to negative 18, x equal to negative 18 divided by negative 4. So x is equal to 18 divided by 4 is 4.5. So we can say 4.5 or 4.5. 4.5, so we've got that one. And then x minus 3 equal to 0, x equal to 3. So now we can create our intervals just like we did with quadratic inequalities. So from negative infinity to 3, from 3 to 4.5, from 4.5 to infinity. So we now have our 3 intervals. We're going to test them out and see which ones work. 0 is going to be easy there. Make that one 4. Make that one 5. Well, if we plug in 0, then we have 6 over negative 3 or negative 2, which is not greater than or equal to 4. So that's no good. No good. If we plug in 4, 4 minus 3 is 1. 6 is greater than or equal to 4. That's correct. And if we have 5, 5 minus 3 is 2, so we have 6 divided by 2 is 3. 3 is not greater than or equal to 4, so that one's no good. And now we look at, is it a strict inequality or not? And we've got greater than or equal to. So we're going to want to check out both of these. And as I told you, those should both work because of that non-strict inequality. But let's just make sure. So if I plug in 3, oh, we got a problem here. Remember I said, what's the other condition? We cannot have an endpoint that came from the denominator. So we can't plug 3 in because we go 3 minus 3, that's 0, that doesn't work. So that's no good. So we cannot include 3. Well, let's try 4.5. Where did that 4.5 come from? That came from the top, so that should be good. So 4.5. 4.5 minus 3 gives you 1.5. 6 divided by 1.5 is 4. 4 is greater than or equal to 4, so that's good. So 4.5 inclusive. So we're from 3 to 4.5 inclusive. I'm sorry, that marker did not show up well for that little part there. So let me just trace over that. So from 3 exclusive to 4.5 inclusive is our solution to our inequality. Well, that was fun, but let's do another one. Maybe make it a little more complicated. 3x plus 1 over 2x minus 3 less than 4. So starting out there, remember we want to get 0 on the one side and get it into a single rational expression on the other side. So we're going to subtract 4 from both sides. 3x plus 1 over 2x minus 3 minus 4 is less than 0. Need to get that common denominator, so we're going to end up multiplying the top and bottom of this by 2x minus 3. So we have 3x plus 1 minus 4 times 2x minus 3 all over 2x minus 3 less than 0. Distribute that through. 3x plus 1 minus 8x plus 12 over 2x minus 3 less than 0. Combine like terms. 3x minus 8x gives us negative 5x. 1 plus 12 gives us 13 over 2x minus 3 less than 0. So now that we have that, we can set both the numerator and the denominator equal to 0. We can't factor them anymore, so that's as far as we can go. Negative 5x plus 13 equal to 0. Negative 5x equal to negative 13. X equal to 13 fifths. And then the other one, 2x minus 3 equal to 0. 2x equal to 3, x equal to 3 halves. So we've got our two possibilities. So we're going to create our intervals from negative infinity to 3 halves is 1.5 or 1.5. 13 fifths is 2 3/5 or 2.6. So 1.5 comes first, so 3 halves, from 3 halves to 13 fifths, and from 13 fifths to infinity are 3 intervals. 0 is going to be easiest there, 1.5, 2.6, so 2, 3. Okay. I'm going to switch to red this time since orange didn't seem to be showing up so well. In fact, we can hear that one going to the garbage. There we go. Plugging in 0, 1 over negative 3 gives us negative 1/3, which is less than 4. So that one works. 2. 6 plus 1 is 7. 4 minus 3 is 1. 7 less than 4? Nope, that didn't work. 3. 9 plus 1 is 10. 6 minus 3 is 3. 10/3, that's 3 1/3, less than 4. No, that is not. Oh, sorry, yes it is. I'm looking at it the wrong way, of course it is. 3 1/3 is definitely less than 4, so yes, we're good. For some reason, for a moment, I was thinking greater than. That's okay. So we found our intervals that work and the interval that does not. It is a strict inequality, so we don't even need to bother testing the boundaries. And we come up with negative infinity to 3 halves, united with 13 fifths to infinity. And that is our solution for this rational inequality. Now, if we took it a little further and did a little more work, we may run into things where we have to do some factoring to give us some additional ones. I don't see that I have one on my paper here, so I'm not going to go into that. But it's the same idea. Look at the numerator and the denominator once you get it into an individual rational expression. Factor if you can, or do whatever is necessary to solve the numerator, solve the denominator, to get your boundary limits, create your intervals based on that, test a value in each of those intervals, then test your endpoints. If you have a non-strict inequality, with a strict inequality, you never have to test your endpoints. But if you have a non-strict inequality, less than or equal to, greater than or equal to, then you must test your endpoints. And you will never include an endpoint or a boundary that came from your denominator, because that would give you a divide by zero. So that can't happen either. So those are the steps, and that's how we go through it. And this finishes up inequalities.